Okay. Thank you. So, all the friends online, all the digital friends, welcome. So, welcome to join us to this special lecture. Actually, I would like to first introduce the guest today, Jason Oliver Vollen, who is a PhD and Senior Vice President and Director of iLab from AECOM. AECOM, as all of us know, is one of the biggest design company over the world, all over the world. And actually, we know I know Jason more than 10 years. Actually, the friendship from the double degree program between Tongji and RPI, and also today Shen Xiaofei, who is our alumni from Tongji, used to graduate from this very special program. And 10 years ago, when we know Jason, who actually played a very important leader roles in both SOM and RPI, especially on the low carbon and the sustainable design. And I think from 10 years ago, he actually moved into AECOM. And I heard that he actually played a very important leadership over the past 10 years, not only in AECOM, but also have a very good reputation in the academic world, on the sustainable and the zero carbon design and this research field. So he actually working in iLab, which is based in AECOM, where he directs the innovation lab as a practitioner. He focuses on the leveraging in the interaction of building technology, finance, and police and politics to deliver high performance and sustainable design solutions that reduce both embodied and operational carbon and deliver zero net carbon capable designs. As a researcher, Jason actually especially focused on the architecture science, and actually primarily he very focused on the next generation building envelope development and the emerging material technologies, where he takes an integrated approach, utilizing the first principle of building physics in order to provide the lower energy intensities that coincidence with improving occupant comfort and well-being. And Jason's research has been funded by NSF Foundation and DOE, NREL, NYSERDA, and AIA as well. He also won numerous awards from AIA and also the patents for next generation building system design. So today, he would like to deliver a special topic on approaching zero, AECOM's hunt for high performance and low carbon design. So let's welcome Jason to give us this special lecture. I think it's we have some guests actually all from my research team, including the postdoctors and PhD students. They actually, most of them focus on computational design and robotic fabrication, and also on sustainable smart material research field. So it's a great honor for us to have Jason to Tongji University. And also, I think over the past 14 years, we established the Futures platform. We have over 800 lectures online on YouTube, both YouTube and Bilibili, international and Chinese platform. I think we would like to assemble the future building technology knowledge from this platform. So thanks a lot for the contribution from Jason. Let's welcome. So the screen's up, please.
Thank you very much. It's really the honor is mine to be here. It's very special to be invited and speak with you today. So for the Innovation Laboratory is the culmination of many years of work. And it really was put together formally about 3.5 years ago, with the idea that we wanted to change the culture of how we design at AECOM, but do it through looking forward at our clients' challenges, some of the challenges that they know that they have, but don't know how to solve. And in some cases, they're challenges they don't know that they have yet, that we're going to help them understand that they have these challenges in the future. So it is meant to be forward thinking, and therefore innovation for us is defined in a somewhat narrow band. And I'll talk about that in a few minutes. Oh, I'm changing the wrong one. Let me try this one. There we go. So I think as designers, we're always hunting for something our entire careers. The history, from my perspective, originally started in materials and methods, and then actually digital fabrication. I've set up several digital fabrication labs in multiple universities over my career. Before I joined AECOM, I was a professor for 20 years, so I did a lot of work there as well. And the search has over those years has led me down a path. So first was materials and methods, then digital fabrication, then energy and digital fabrication, and then ultimately in energy. And maybe it'll come back around to materials. And today I'll show a range of those things. We're not going all the way back, but we're going to have a little bit of history to help talk about the philosophical underpinnings of why we're focused on what we're focused on. So it's really built in 4 parts: innovation as a service, iLab innovation projects, research that's building envelope as the energy transfer function, and Back to the Future, AECOM's high performance design, which is really the speculation of where I think we may be heading. It's a speculative future. So I'm going to close this one down. Over here. So innovation as a service. What do we mean by that? For us, innovation is defined as the ability to make an impact or provide value. Why innovation? It is understood in probably every industry, hopefully ours, but ours is a little bit more challenged, as the method for disruptive growth. So why is that important for the architecture, engineering, and design industry? Because of all of the top 20 industries, we are the only industry that has become less productive in the last 100 years. A study came out from McKinsey about 7 or 8 years ago that showed, including agriculture and medicine, all the major industries have increased their productivity. We have decreased our productivity. That's a pretty challenging report card, because of the weight we have as designers on the world, and all the things we see around us come from us. And if we're slower than everybody else, we're not keeping up. And we also play a large economic role. So the faster we can do work, the more we can help drive the economy. And when it comes to climate change, the rate of change of our discipline is critical to participating in resiliency and sustainability long-term. So we have to build more, better, faster. Otherwise, we're going to continue to fall behind, and it's going to be harder and harder to address climate change and sustainability. So for me, it's very personal that we want to find ways in which to do things better when we can. So a lot of what we've been trying to do from a cultural perspective across AECOM is talk about innovation really in a couple ways. These are two models of laboratories. On the left is the understanding of the world in the 1400s. It was a sea that was flat, and you could sail. If you sailed far enough, you'd fall off the edge. And if you fall off the edge far enough, a sea monster would get you and eat you, right? That was the understanding 600 years ago. And to the right, you see the sliver there, that's Sagres, which is in Portugal. It's the westernmost part of Europe, where Prince Henry the Navigator in the 1400s brought artisans, engineers, designers, and craftsmen together in really the first multidisciplinary school to develop new tools to travel the sea and go beyond the edge. So it was a journey that they were taking on, and they didn't know where the end of the journey was, but they knew that they had to go to this journey. They had ideas about where they were going. In order to get there, they had to invent new things, and in order to invent new things, they had to have multiple points of view. On the right is the outcome of the Jet Propulsion Laboratory in NASA, which is the first manned space flight to the moon. And that's one of the most recent important events in multidisciplinary teamwork. And what came out of that were things that we use all the time today to help us think about decarbonization. LED lights came from that work. CAT scans came from that work. The dust buster to suck up moon rocks came from there. So an enormous amount of digital technology and new devices came out of the desire to go someplace you're not sure what you'd find. So part of the theme is with innovation is to take on things where you don't know the answer to. And in order to do that, you need a very structured approach, because otherwise you're just trying it and you don't know. You could continue to try and fail and you won't learn. So the structured approach to innovation is really critical. So we think about that as in the institution, really in three ways. Thriving innovation occurs when the strengths of the organization are leveraged through intentional innovation to achieve the organizational vision. You could look at both the Oceanic School of Navigation and NASA and JPL as having that same mission. So from our perspective, innovation takes practice, and it is a practice. Just like you practice architecture and engineering, you practice innovation. Healthy innovation is the recognition of the universal value of it, with a shared understanding and belief showcased by a broad commitment to multiple organizational levels. In other words, good ideas come from everywhere, and it's really critical to bring everyone at the table early, right? And that's how we're going to solve things. And none of the work you're going to see today was done alone, and none of it was done only by me. A lot of it was done with Xiaofei, probably the majority of it, and couldn't be done without him and other people working together, looking at different viewpoints to solve it. So innovation brings value, but it also is a value of ours. And then innovation grounded in the design thinking process is the development of solutions, products, processes, and businesses through a robust framework with a focus on unlocking and creating that value. So innovation requires discipline, but it also is a discipline, right? Like there's a practice of architecture and a discipline of architecture. We believe the same for innovation. Now, there are some, we can look to material science, which 60 years ago didn't really exist. It was always the school of mines. Was material science came out of. Before that, it was just about mining and geology. And then at some point, it turned into material science and it became very different. That also changed the world. So that's a very new discipline, material science, you know, in the history of universities. Innovation, I think, is that next piece for us. So how have we thought about innovation in what we're doing at iLab? One thing is to take on the challenge that the world is taking on, which is really decarbonization. Whether you feel that it is a big problem or a little problem or not your problem, it is at least a conversation that everyone is having globally. So it's an opportunity to have those broad discussions, and you can get some wind at your back to see how far you can go. So from our perspective, we are you take an idea or a good solution in and of itself, we feel like that's not innovation. But once you prototype it, test it, and it's shown value, then it's an innovation. That's kind of the marker for us. And so we're looking at this at 3 scales: the city scale, the building scale, and the system scale. I'm going to show a couple examples of each of those. And each of those, and each of the approach actually is somewhat similar. The content is different and the modules are different, but the way of thinking is there. We often talk about tools and digital tools, but the reality is this is a change in thinking and workflow. There's a technology layer that augments the workflow that allows us to do things we couldn't do without that layer. But that technology layer is what I'll show you, but I'll try to make it clear how the thinking is different. And that's what really the paradigm shift is, by bringing innovation as a discipline to the design. The other thing that this allows us to do is understand the relationship between the system and the city and the building at the same time, rather than in a very linear fashion. So the way we work is to, with clients, and clients for us are internal clients, are internal practices, but they're also external clients. We work through ideation and research. to develop what we think will be an innovation. We test it and optimize it to see how well it will perform. And ultimately, we customize it project by project. And this customization is really important because that's more like the design process. You don't do the exact same process for different buildings, right? You change your process, you change your result. And therefore, we think the technology layer also needs to change to adapt to be more precise. So if you buy a piece of software, it kind of gives you the same result. You just have to use it differently. We change the software by project, and that's a little bit of a different approach. And then in the center column, you'll see there with the iLab tags, those are all of the different modules, and there are modules within modules there that take on all of those different scales. All right, so the section 2 here, we're going to go through some of these projects. As I mentioned, the critical piece for us is that we're testing them on real projects to show their value. So while in many cases, what we're doing is relatively new, all of these workflows and technology layers I will show are no longer than 3.5 years. They go back farther in terms of ideas, but they're really within the last 3.5 years, we've been developing them, in some cases, last 6 months or less. But we test them out on a range of clients and scales and asset types. So we have greenways in there. We have cities. We have all of the residential homes in the state of Washington, for example, science and technology buildings, logistic buildings, new cities, tall towers, low rise, master plans, airports. That's where it becomes flexible and a way of thinking and customizing that approach for all those clients. So we've tested it out in all of these. There's more, but that's a good sample of the breadth of which we work. So the first one, we'll start at the city scale. This is the Hong Kong new city development. And what we were looking at is life cycle carbon assessment and doing a decarbonization strategy. So ultimately, they have to achieve the goals of the project to achieve carbon neutrality by 2050, and 25 years of total carbon emissions projected to be reduced by 50%. So we've settled on a kind of framework for the technology layer, which is really dashboarding. And a couple of things happened in the development of software, primarily in Grasshopper, Rhino, and Rhino within Revit, that allowed us to build dashboards and connect multiple layers of analysis behind these modules. So there's behind what you're seeing here in the dashboard is the ability to do all kinds of calculations on industry validated softwares so that we can backtrack and confirm what we're doing, as well as databases that are either publicly available, like carbon databases, or databases that we've collected from our knowledge of practice over time. So on the left, I'm going to show a demonstration, but to kind of orient us, on the left is really the importing of the data of the city from the land parcel perspective. We can have carbon results, the time frame that we're looking at for decarbonization, because we always look at decarbonization as the total life cycle, the carbon reduction strategies, and scenario comparison. So what we think is important about this, I mean, there's many things I think that work that are interesting, but primarily in the carbon reduction strategy section, you'll see a few columns here. There is baseline, good, better, and best. That seems pretty simplistic, right? And then here, vertically, are every single system that you can have within the city framework that helps make up this master plan. So why do we do good, better, and best? Because we realize that we know more about the solutions before we start a project than we are readily able to admit. I'll use an example from building. When you started building design and you're a mechanical engineer, during the first section, while the architects are drawing, you write a narrative. And then when the architects say, okay, we're moving forward and start to delineate the plan, then they do a single line diagram. And then when you finally get to detailed design, yes, then they're picking a system. But we know the systems options already at the start of the project. So why not bring that discipline and their knowledge up front to the early stage modeling? And so we ask our engineers, what's the baseline that meets the minimum requirements of the project? What's a little bit better that's available on the market? What's a little bit better than that? And then give me the one that's the most advanced that you possibly could get. And we could look at it That way, in terms of improved efficiencies, more radical design, more radical performance, or we could look at that as timeframes. Here's what we can do today. Here's what we can do in 10 years. Here's what we can do in 20 years. And we can model that. We know we can select those systems up front for each one of those disciplines. And that allows us to find out, should we be targeting baseline, good, better, or best? And what we found out is sometimes baseline is good enough. It doesn't make a difference whether you use baseline or the best. What connects all of these together, of course, is the carbon impact of those systems. And sometimes the best doesn't help you with carbon. Sometimes it's the right combination. So in the end, we're looking at the bundles of those systems in the levels, in the right selection of those levels. And that, as you can imagine, becomes numerically very complex because there can be thousands and in fact millions and millions of combinations of systems. So in order to address a problem so complex, you need a technology layer that's built to handle complexity. And that's why computation becomes an absolute critical part. You could not do this analog, right, in this way. I'm not saying you can't do a master plan, you can't build a city or a building analog, of course you can. You can't do it this fast with this amount of surety by reducing the risk and understanding what the cost projections would be without computational needs. So here, when time, the challenge here is time is a critical factor for influencing success. We need to make change fast. And if we can make better decisions faster, we can't always, this may change with robotic construction, but for the moment, it's difficult to shorten the construction phase, but it's much easier to shorten the design phase. But how do you shorten the design phase and make sure you're doing a better job rather than a worse job? That's really the challenge. And that's where this good, better, best comes along. And you can see as you begin to select these pieces that the carbon will begin to move as well. So it works in real time that fast, right? And so we can individually select using our intuition and knowledge as disciplinarians, or we can automate that. And we can run thousands of selections of bundles. And what that allows us to do is create scenarios and track that, the graph you see there, about where we think over time, in this case out to 2050, we think we will be if we do nothing and don't make any change from business as usual, or different selections of bundles that will allow us to create profiles of the performance, in this case, at the city scale. So the idea of multi-objective optimization is, we're finding, is really critical when you have potentially thousands of variables and then those combinations end up in the millions. So if we look here to the design components, the baseline strategy and the good strategy, and then in the center, we have a cost component and a carbon component together. We run thousands of options, and you can see the Pareto frontier here that's tracking. We need to get to this, we need to be below and over, and we end up getting much fewer selections. If you had to try all of those out, how long would it take you to figure out how long it would take you to get to B? And you're not sure where you're starting, right? And that's that voyage that we're going on. We're not sure where we end up. We know where we're going. We understand the criteria. We need tools to help us get there faster. We can start by selecting the parcels. They're loaded in. We start with assumptions, as much information that we can gather that's available, and then we assume the rest. There's quantities, then there's operational carbon strategies. Again, against that, baseline, conservative, and ambitious, or good, better, best, business as usual. So you have operational carbon, embodied carbon. Then we can see, as you make those selections, the different bundles. And this happens in near real time. What's really engaging about this is when we used to get a directive from a client, and then we would go back to our desks we would work, then we talk to 3 different disciplines and talk to some more, and then we do some more research. Now we do pre-work ahead of time and then sit together with the client and do this together. Where do you want to go? And ultimately, you can see there are a series of bundled selections on the right, and we can choose how much carbon is necessary for us to reduce. Ultimately, what might be the cost of that? What are the stops along the way? And down in the bottom, you can see the kind of scorecard against the things that the stakeholders, it's really not a client when you're dealing with a city, right? It's stakeholders, right? What do the stakeholders care about? So there's a pattern that comes out, and we can begin to quickly assess which is the right pattern for those stakeholders. And then, of course, there's very quantitative data. We've also found that those stakeholders read things very differently. So the communication of these ideas is really important. Some stakeholders read numbers, some read graphs, some read patterns, some listen to words. So our approach is to show them all. And that gives you the total picture of how you understand the information flow giving you the results. So this is an example now, of course, at that huge master planning land use scale of what we do all the way through. Yeah, better go back to that. Okay, so that was the city scale. Now we'll zoom into the district scale. So there, before we were looking really at land use information. Now we're going to be looking where there actually is building envelope information. This project is called The Point. It's a district in Utah. It was designed by Skidmore, Owens & Merrill, but they had a very difficult challenge, which was to meet or exceed 50% carbon reduction, including other KPIs, which we'll discuss, but no more than 5% total increase of cost over business as usual. So very little cost increase, but a lot of carbon reduction. So we were engaged with this process we call Sustainable Systems Integration Model, RAPID. It's now cloud-based. And what they care about here is carbon, waste, energy, smart capability, integration, water, and vehicle miles traveled. All of those help with the sustainability and usability and livability of the district. And those set the targets by which we want to measure the decisions we make. So we have the model and a plan, the urban systems we care about, and that baseline good, better, best scenarios. We do iterative optimization and get alternatives. From those alternatives, we can engage in the sustainable systems model, which is what I'm going to show in a minute, and then smart city technologies that can help augment that. And then ultimately resulting in your key performance indicators and the cost of those key performance indicators, so that can be capital planned into the development of the district. Not understanding how to spend your money is another huge time delay in the productivity of the built environment. If we understand the capital flow over time, we can make decisions and start work sooner. And ultimately, that should give us choices on what is the program that we should put in place to maximize those stakeholder values. So starting from the digital twin, which you probably hear a lot of these days, we're starting to call it the living master plan, because digital is not something extra now, right? It's all digital. And we want it to be living, and it changes over time. So the a priori condition is where we start. And then as it develops, that continually feeds the model. And that's why I consider it living and digital at the same time. We get the strategy selections, integrating in with smart city opportunities. And outcome of that is the performance metrics by sector, and then the division of capital expense and operational expense over time. You can kind of see a blow up there of those different criterias. And the key part that's valuable to the stakeholders is they've set the goals. We now have results, and we can checklist against it very quickly. So we can say, how, with all of those different variables, are we meeting the goal of the project? And to blow up there, you can see we kind of can break down as the baseline reference. Here's to meet goals. And ultimately, how far can we go? How much lower can we go in terms of reduction in carbon? But what are those cost impacts over time? And really importantly, when you're dealing with district and city scale, is where does the CapEx come from? Where does the money come from? It doesn't come from one place when you're developing a district. It comes from multiple sources. So to be able to understand who has to fund how much in the early stages of design is really critical for setting up the funding strategy for the development. And it looks something like this. So you can select here, scenario 02. We're loading the scenario. We have the model. Each of the parcels or building models there contains data. So we'll go to the 2D, and as you select it, you get the data that's built in. In this case, the expected energy use of that type. Now we're looking at water. Sustainability performance overall, and so that becomes the selection. Now we're changing from good, better, best. Now, good, better, best is defined very technically in a spreadsheet that's behind there. So it's not just a percentage, it's actually something that's articulated and modeled. That was building energy, photovoltaics, public realm, street pathway lighting, for example. Move over to smart systems integration by the percentage of fully integrated or partially integrated systems. Electric vehicle adoption, smart parking, all of the components that make up the district become part of the model. Waste, and then it calculates. And we find out how are we tracking against the original target. So move into another scale and a slightly different type of project. In this case, we're looking at really single family homes at the state of Washington. We were engaged to help them create a plan for 95% carbon reduction for 3 million households across the state. To do that and model those individually, that would be really difficult. I think if we calculate it manually, it was something like 84 models we could do. But when we did it numerically, we could do 180,000 simulations in the same time. So we can get a much higher level of resolution by doing this bundling and modeling. In this case, we're fetching data from publicly available resources of the systems and then engaging that and extrapolating that to the home types that are available. And what we understand already is with these system selections, none of them are meeting that criteria by the 2050 goal. Many of them can meet the 2030 goal of a certain amount of reduction, but none of them alone will help you get to the 2050 goal that's really required, except for these systems here. So immediately we can understand what systems do you need to move to in your building. The good news is most of these systems are already under the line for 2030. So they don't have a 2030 problem in the state of Washington. They have a 2050 problem. And because they know they don't have a 2030 problem, they don't have to work on that problem. They can immediately start working and buy themselves an extra few years to work on that 2050 problem, because those systems are harder to institute. They're more sophisticated. They're not as readily available. So they need more leadway time to get there. In this case, we're training a model using machine learning from the publicly available records. What you just saw was the dashboard. We get the modeling results, and then future developments learn from the database. So they're being planned, the new developments are being planned based on the data they're getting, and then that data will feed back in to the new records, so it will continually refine itself, ultimately machine learning over the time on the way to 2050. So you can see here how far we can get from our model. By 2030, we've got 65%, and by 2050, we can get 96% based on the results and those 180,000 simulations that we've got. And then ultimately here we go, the 64, it was 64 models from the original approach as designed. And then we came in, developed this process, and we got over 180,000 models that allowed us to get to those results faster. So a little bit of detail here, for example. So what you'll notice that always on the what's meeting the goal here on the right-hand side for 2050, it's always electrified. So electrification is the future for buildings. There's no way around it. And so we now that we know that, it's clear in the model that you cannot get to the target reduction goals unless you electrify. We can start working towards that immediately, right? In our cities and our infrastructures. And in the United States, this is critical because the electrical infrastructure is not ready for an electrified built environment, which means that if you start electrifying all your homes, your infrastructure will fail. So what does that tell us? Don't focus on the homes yet because 2030 is fine. Focus on the grid because the grid is not ready to handle the load. So we'll zoom into the building scale. This is the National Renewable Energy Laboratory EMAPS building. So it's a research building for energy storage. This was a competition done with a contractor. So it was design build, therefore we worked for the contractor. And our role at iLab was to be the integrator. So often when we're engaged in building projects, we sit between the contractor, the architecture designer, and the engineer. And we ourselves have different disciplines. Architecture is a central one, but we have a bunch of different disciplines in our group. But our job is to know enough about all the different discipline languages that we can pull them together and bring that collective knowledge up front into the model. You kind of see the building here. The types of challenges you face here is it has to be a very high performing building with the potential to be net zero carbon, so net zero carbon capable. But to build the building, you have to really build the majority of it out of concrete because it's the cheapest material to meet the requirements of cost, which was a set cost. So you're seeing here an atrium that is done in mass timber, but it's the place that you enter before you go into the concrete buildings on either side to help discuss what the building is trying to achieve. Of course, the architect wants an all wood building or a fabulous facade. Sometimes they don't care what the facade is as long as it's expensive. The contractor wants is as cheap as possible. And what we're trying to do is help them find the balance between the two. In this case, you're looking at the same as the dashboard becomes familiar. Inputs on the left, strategies in the center, and then outputs on the right. We often try to get some free support, which means massing and orientation often allows us, when we do it, again, computationally, allows us to make choices that don't cost anything. And so we want to do that first. That's, this technique has been around for quite a while, but it's not used that often in many offices. And we actually think that you really can't do a project of this complexity, manage the cost and increase the performance without doing this kind of modeling. So we can run thousands of models looking at daylighting and energy. And the result of picking, from the, again, kind of greater frontier, maybe we're looking for, A3. How do we know A3 if we weren't doing this computation? That's the one that's going to be the most supportive what we need to do. It turns out that the version of A3, from looking at it from this multi-objective optimization, allows us the same amount of solar photovoltaics on the roof, 10% less facade cost, 5% less building energy, and an improvement of 2% in natural daylight without spending a penny, right? So we're starting off towards zero without costing anything. And the facade plays a large role in this. I'm sure 50% in a building like this of the energy is gained or lost at the facade. So the performance of the facade really I look at the facade as an extension of the mechanical system. And when I show my research in the next section, you'll see it is essentially a mechanical system. So the challenge again is using the facade impact tool, we're zooming into this scale where we can look at cost, daylighting, and energy together with specific assemblies. How do we choose that right assembly? In this case, a typical sandwich panel would be a certain width of concrete, then there's insulation, then there's more concrete, and then there's framing with insulation so that you can put things around it. And that together will make a performing enough, but very carbon intensive wall section. And the cost is cheap because it's mostly concrete and insulation. So with our analysis, we found out by adding 1 inch of insulation and changing the type of an available insulation, we could then remove the inside framing and then remove the inside insulation so that it was just concrete on both sides. And that performed equally as well. And you got the added benefit of thermal mass on the inside to stabilize the temperature. So then you got effectively a radiant passive mass throughout the entire building, which improved the performance of the energy model. What's important about that is it also reduced the cost by millions of dollars by not having to add that extra layer, and sped the process up because you don't have to have extra trades in the building. So of course, the contractor's thrilled at solutions like that. What we find often is they're the ones who hold the note on the project. They're the ones who are accountable to the client for spending the money. They like the cost certainty. That's really important to them. And if we can meet the sustainability criteria with their cost certainty, that in the early stages of a project, they're happy to do other things. Oh, you save me money here, go make a lobby made out of beautiful wood, right? You can go spend it there. So that's that kind of exchange that we sit in the center of when we work this way. We use the same type of approach in trying to equalize the daylighting. There's many daylighting analysis tools. I think for me, I've always worked towards finding the lowest contrast across any particular space is the most comfortable from a well-being perspective and increasing the productivity of the people in the room. So we're looking to reduce hot spots and reduce dark spots. And oddly enough, it could either be all dark or all light, and that's better than dark and light at the same time. So we're looking to try to create the evenness. In this case, we tried out multiple roof types until we arrived at a kind of combination of 2 clear stories in the lobby, plus a reflective panel that then brings light deeper into the floor plate, reducing that contrast ratio across the entry space. Just to take you through the process that we went through with the design team and the contractors. Can geolocate the building. We can select the criteria by which we're creating the code. In this case, it's the building code of 2021 and ASHRAE 2019. You see, we can adjust the massing and the structure. What the wall area is, we can do window wall ratio. Up there on the upper left is selecting the modules that we look at. And then good, better, best, looking at, in this case, we're looking at operational carbon. It already went through the body carbon. You can see as you make those selections in real time, because these are pre-engineered, we know the system, it's already been modeled and then linked here through a database. It's important to note that we see this as a design tool and not a carbon tool. Carbon is the measure of efficiency. Ultimately, how good your design is, how low your carbon is, how well does it perform? That should be the test of how good a design it is. It's not, carbon isn't necessarily the only goal. It's also daylighting and usability and views. And so we like to bring those things in there as well, both quantitative and qualitative aspects. And we can model the scenarios between the baseline and the individual pilots of those different selections. So we can see how is one improved over the other and what the relative costs are. We can select the key performance indicators, what the stakeholders care about. In this case, you're looking both at the end use client of NREL, but also at the contractor, since we actually work for the contractor. And you can see the different ways in which we can adjust. We go all the way for best, you can start seeing the shape change. So you kind of get a pattern recognition ultimately of how well is this performing. Now we're going to zoom in one more time to the system scale. This is a project that we worked on 2 years ago, where we were developing what we called the facade impact tool, multi-objective optimization. So FITMU. And the goal is to increase efficiency and try to manage the cost at the same time. So in a similar way, looking at the fenestration, shading, the wall assembly, the outputs of daylight, energy, cost, carbon in a series of the baseline as designed, and then scenario 1, 2, and 3, which can be done both manually based on our intuition. Often, I mean, if you've been doing this for as long as I have, sometimes you kind of know what the pattern is, right? But you don't always have me in the room. So you need to be able to provide numerical ways to get there. So our criteria here, linking together climate analysis, input parameters for the facade, the performance simulation, which is really two parts of the dashboard, and ultimately the multi-objective optimization will help yield the results in those two frameworks. And then you'll see side by side the facade optimization, the facade impact tool on the right, and the multi-objective optimization dashboard on the left. Other way around. So on the left, you're looking at the impact tool, which is looking at the facade selected in the built context, brought into the bay scale. You can look at different orientations to very specific wall assemblies as part of that. Each of those, because it's a discrete assembly, it's easy to cost. And that cost can be from information we already have, or it can come directly from the market, from the manufacturer. And on the right, we're looking at running thousands upon thousands of scenarios of the window wall ratio and the makeup of those performance aspects of that assembly, so that we can see which one of those makes a difference when you move the sliders around to say which part of the performance of that assembly is critical, and then how does that impact energy and daylighting. And then ultimately the results are that by deploying the facade, we have three types there on the right-hand side over there. You deploy those strategically based on the profile loads of the building. And we can, with a little bit difference in carbon, so the carbon increases a little bit, but a significant decrease in cost. So we think that's valuable because, again, it helps us. We can put more money to use towards something else. Maybe for that money, we can put a much more efficient mechanical system in the building, for example. So that's the kind of trade-off we're trying to get to, deploying those facades strategically, understanding what people care about. Everybody cares about cost. And again, carbon as the indicator. In this case, it's the lever that helps us make those choices. We began to think about it this way. This is a project that we worked on in New York City. A client came to us and said, make us the best building in New York. And so we worked for a little while to try to come up with a strategy to do that. I don't know what it means to make the best building in New York. There's a lot of buildings. There's a lot of great buildings. But the criteria we chose were energy, photovoltaics, and view shed. Because in New York, the real critical aspect is what you're looking at. That's the largest economic driver of the ability to sell or lease your space is what that view is. So to maximize all of those things together, we created a suites of banks of windows. I think there were 5 different types of banks. We were kind of detailing 3, and they were deployed strategically around the building based on the criteria that you could see. And then ultimately it looks something like this, which this is really the expression, everything in the kitchen sink. This is every system you could possibly throw at a facade, we threw at it. We don't necessarily think that that's realistic for most projects, if any, but we wanted to showcase what they could do if they wanted to address all of those criteria at the same time, and ultimately allow that facade as a performance facade to have an aesthetic that can brand the building and brand the company as they started to build more buildings. They're a Dutch company that wanted to do work in the US, and therefore the branding of who they were as a wellness and sustainability company that allowed them to get higher lease rates was absolutely critical. So the facade performing, reflecting that performance becomes that advertisement. And something like that. I don't know if that's the best building in New York, but it's not a bad building in New York. And it is, it does have something reflective about the city in the way in which it's performing. So there's an aesthetic that you can come to from the outside that you don't even need to know what it is, but it's specific to something. And I think that's meaningful rather than composition. And then, okay, so finally a built project. This is a project we started working on in 2017, which was a STEM building, a science, technology, engineering, and math for a community college, Suffolk County Community College. They wanted net zero energy. They needed cost control, and there was a very limited, almost unrealistically low budget, and it had to be a legacy design building. And that's very difficult to get all of those three things at the same time. And in fact, what you're looking at is the result. We had things we had to pull out of the building because of the cost constraints. But in the end, the major idea here that you can tether the sun and the earth together through the shape of the building can create meaning that reflects what you're doing in terms of water flow and solar harvesting at the same time. And in the end, what we looked for was the sweet system of selections that allowed us to get to net zero energy that you could procure today. So it didn't have to be, if you select systems that your client can't manage, then the systems won't work and your building won't perform. So it's something critical that we've learned along the way is making sure that we pick systems that the client can manage over time to make sure that they run at optimal performance. So we had to pick ones that were already available and out there. And to help us tune the envelope, we used similar computational techniques. In this case, we can run a suite of protocols to help us understand the solar shading on the south side, which we've already reduced its exposure because of the angle. And in this case, we want light in, but we need to control that light because every ounce of space is valuable because it's limited cost. So each space is used. In this case, classroom or lecture space, even if it's on that south side, has to be used for something functional. So we need to control the light. This allows us to precisely articulate that facade to the purpose of the building in the environment that it's in. And here we're doing the same thing with the windows on the north and west sides. Where should the vertical shading go and the pattern of the windows so that we can create the most even quality of light in the room where they're going to be working? That is challenging because you're working on screens. They're teaching cybersecurity here. So they're all looking at screens, but there's a lot of light. You can imagine the glare that could happen on the screens if you don't get this right. So this is a critical aspect of finding out the right pattern of those individual components using the same technique we did for major parcels of land in the first project that we showed. The workflow and thinking is not different, but the scale is different. So we're going to shift pretty radically for this next section. There are a lot of slides here. Some of these I'm going to go through pretty quickly. This is work that I did during my PhD at Delft. Which was, I've worked in architectural ceramics ever since undergraduate. So I've been focused on the value of how you can use ceramics initially first through aesthetics and longevity, but ultimately I came to understand the value of articulating a mass with a certain shape, that the fluid dynamics around that mass can play a very important part in the energetic nature of the facade, where the facade does become a significant augmentation to the mechanical system of the building. There is enormous amounts of energy that flow around the facade. They're very low-grade energy, and typically you wouldn't use it. You want to get rid of it. But in this case, we want to use that building facade as an energy transfer function. The trick is you often don't need the energy at the same time it's available. So that function has to have a time delay in it. And regular passive mass, it's very difficult to control that time delay. So we need to have active mass. And I'll talk about what that is from my perspective. The main part that you're missing there is the kind of catchphrase where it starts, which is called climate camouflage. The goal is to use the building facade to camouflage the building from the energetic forces of the environment and make it feel like it's not there. So this is nothing new today, right? The weather tape. But when we started doing this like decades ago, when we had to run this and run these things for the first time, and software didn't do it for you, it was really important to say, wow, this is the real pattern of those criteria that are driving the environmental design. Initially, this was done writing our own code. Eventually, most of the softwares do it for you, right? I think what was most important for me in this is when you're thinking about passive and passive hybrid active design, it's not so much the energy that's available. There's always energy that's available. It's the frequency of that energy. How long is it? From what direction is it? And do you have the right approach to harvest the particular frequency? Here, you're looking at sky cover there, the kind of gray third line down. It's really the frequency moves a lot up and down, right? You can take this same climate and go to, say, Abu Dhabi, and it's very even because the frequency is different. And that would mean you'd make different choices with the facade because of the frequency and the type of change of intensity of that energy around the facade. So that sets up the kind of criteria of trying to effectively hide the building from the forces by capturing those forces and redirecting them. So the title is Countercurrent Heat Exchange Building Envelope Using Ceramic Components. So to start, on the left is another view we call the climate clock, which is looking at all of those same criteria, but in this case around the annualized year, heating and cooling. We're running this now, in this case, New York, but I'll show some comparisons. The building envelope, which needs to navigate between thermal comfort and climate clock. And that ultimately is the conceptual challenge, right? This is not, it's not anything we don't know that this is the criteria. We're just trying to put the right, understand what are the things on either side of that envelope and what can you do with the envelope to begin to match those things up in new ways. So if we look at, if I can hide this thing at the top. Do you know how to hide that out of the way? Yeah. Broadly speaking, you have layered assemblies of building envelopes and mono assemblies of building envelopes. And they evolved into combined systems where you get like the range screen wall, things we typically use today, range screen wall, thermal mass sandwich panel, I described that earlier, integrated concrete formwork walls. And then you have, that's coming from the mono assembly and the layered assembly combinations. And then where I'm interested in is the integrated or polyvalent wall, where you have both active and adaptive. What I'm focusing on is A2 down there, which is the adaptive facade, the ability for energy to move back and forth through the envelope in a controllable way. The driving statement is countercurrent heat exchange building envelope using ceramic components reduces the peak energy loads that contribute to energy use intensity of commercial buildings. And as a question, what is the energy use intensity reduction potential of the thermal adaptive ceramic envelope system using ceramic components for commercial office projects? Now, I had the opportunity to teach in a PhD program for many years before I did my PhD. And I learned this maybe too late in my teaching career, that asking the right question is the most important thing you can do when you're doing your PhD. If you don't get your question right, you're gonna have a very difficult time. I spent a lot of time doing that particular question and refining and refining and refining until it was a very narrow band. And yet this is still a design, ultimately this is a design project. So again, the criteria of energy that we're working on here is there's a typical commercial building here 3 times a day that energy use by sector is being used. You can split out by annual up there and then 3 times in one day. And what you're looking at in the kind of shaded gray areas there is what I'm targeting. That's the energy use I'm trying to take off the books to camouflage from the facade. All right, so there's a couple precedents. So this is not the first time this has been tried. This has been tried in many different ways. So there's building integrated, you can see there BIST system. So this is air-based, where you have a series of different layers. You see exterior and interior. This is a range of different typologies where airflow, which is effectively the same as fluid mass, moving through those cavities as an active insulation. This is the same thing as liquid-based, fluid as well, but liquid-based, so air and liquid-based collector types, where you're collecting that energy. All in the attempt to do the same thing I'm talking about, right? So again, I'm not inventing the concept. I'm trying to use very specific components of that concept that I'll show in a minute to augment an idea that's already been really around since the Roman times, because that idea of the hypercaust, which was where you were heating the floor of the building and the exhaust would go up around the walls, is not so dissimilar to what we're looking at here. So it's an idea that's thousands of years old in practice. And ultimately combination types of fluid collectors and fluid passages. So where has this been used before? Up on the upper side, that's the hypocaust. Those are the chambers you can see underneath the floor. You light a fire. Effectively, you light a fire. That fire pulls the heat and gases through, heats the building and up and exhausts out. So there you're effectively making an actively heated building through the chambers of the facade geometry. In the center is the Edge building by OVG Real Estate in the Netherlands. At one point, before the Bloomberg headquarters in London was known as the most sustainable building in the world, until the Bloomberg headquarters, which beat it out in the BREEAM scale by maybe a few percentage points. It used active cooling panels in the ceiling. So you see the ceiling panels down there, there's actually polypropylene tubes in there. And so they're actively cooling, using radiant cooling, which really what it means is it's exhausting heat through the fluid. You feel like it's getting colder, but really cold is just the absence of heat, right? That's our building physics note for the day. And then below is a demonstration factory at the University of Darmstadt, where they do something similar, where they have pipes embedded in these concrete panels. And those pipes then go to collectors and go to seasonal storage and then are pumped back out. So this is, it's primarily a net zero energy, fluid embedded factory building that holds its temperature over the course of the year. And it's actually quite comfortable inside. So there are precedents for this as well. So what I was interested in is doing this out of ceramics and ultimately looking at very particular parts of what's happening in a building facade. So the functional aspects are conduction, convection, capacitive storage, mass energy transfer, radiation, refraction, reflection, and human thermal comfort. So those are the equations that are driving what's happening in that building facade that's navigating the outside climate and thermal comfort. That's a lot that's going on there. The parts noted in red, those are the variables that I'm trying to control to create more capture or more release or time delay, and create a ceramic component of the facade that is able to harvest all of those things. So here is kind of conceptually how a ceramic tile has a large dimension to it from the building, how you begin to articulate those different components to maximize those variables. Should it be more of it or less? And so you could look at it like this: material thickness, right? It has to do with capacitive storage and conduction. That's the material. The color has to do with radiation and reflection. Texture has to do with convection, roughness, and surface area. So remember, there's an equation for each one of those, and they all have to function together. The orientation has to do with radiation. Thermal exchange is energy transfer, temperature, and mass flow. And energy transfer as a system, when you assemble them all together, is capacitive storage, temperature, and then the time constant or flow rate. Ultimately, creating an adaptive ceramic module that takes advantage of those energy flows in and out of the building. So now the diagram looks like this. I'm taking energy from the inside and the outside. Some is being reflected, some is passing through, but I'm capturing as much as I can. Of course, I think I'm capturing a lot of it, but we'll see what my results really show in the end. And so in section, it looks something like this. There's a module here. The numbers correspond to the functional what's happening. There's a fluid inlet in a hollow tile. There's an articulated surface area that helps control the exchange, so maximize the exchange of that energy on the inside and the outside. So fluid comes in cold, exits hot. And it can go vice versa in reverse. So we built it using digital fabrication lab. We built molds with those articulated surfaces meant to manage the capture and then transfer of that energy. So you can see there's the outside is articulated. On the inside, you have this we call pin bank, which is really allowing, it's not any different than the cooling computer somewhere in this machine here. There's something similar to it, but now we're making it at a large scale and making out of ceramic. And ultimately, this is a prototype of a tile for a building in New York City. So it's 17 degrees off of direct north. That's why you see the angles. It's maximized for a south-facing wall in New York, but south is 17 degrees off true south. So we were trying to create a more realistic, you didn't want it perfectly south because there is no perfectly south building in New York. One thing that really helped, of course, was with the numerical work was having a company to work with. So I worked with Boston Valley Terracotta to help create a series of prototypes. They have a workshop every year for advanced ceramics, and every year we come with a new design and build a new tile. And we did this 4 years in a row. What you see on the right is the inside tile radiating, and of course the surface in the front, on the front and the center, and then me working with a team of folks trying to assemble these tiles together so that we could test them. This is the second year where we decided to move to an extruded because it was much more efficient way to build. And in this case, we, instead of fluid moving through the ceramic, because really ceramics meant to keep water out, not keep water in, as it turns out at the building scale. So it was much easier to embed pipes. And so we have the heat transfer pipes now embedded directly into the ceramic. On the right side is the inside radiator tile. So it's a ceramic radiator. And the outside is the collecting surface. And those fluid moves back and forth through a secondary. So the fluid doesn't go direct. It heats a separate fluid in a bank, and then it heats the other side. So the transfer of energy is clear, but the fluid does not actually exchange. And it looks like, ultimately it looks like this in a wall section. So you can imagine this is the spandrel panel of a building. On the left on the outside, on the right on the inside, you see the storage tank and the pumps and the radiator. So how does it perform? So we built it, tested it to make sure it worked. And of course, we put a heat lamp on one side, and soon you can see on the other hand side, you can feel the heat. So right, we know it works, but how much does it really work? So we modeled it using fluid dynamics to get what are the right multiple different pin sizes. What are how many pins do you need, and what pattern and what shape? We built a hot box. This is a standardized ASTM hot box test. So you see a chamber on the left and a chamber on the right. The one on the right is the outside temperature. The one on the left is the inside temperature. We deployed 64 thermocouples throughout the space as well as on all of the components and ran the fluid through the system and ultimately charted the results. And the goal here was to calibrate the digital model. So there's a computational model that's calibrated against a physical test. So therefore we could feel like we could then extrapolate from this information. So we didn't have to constantly be doing physical tests every time because we understood how the individual components work. And you can see how the measured fluid and the measured lines and the computational lines track very closely together. So then you have to build the model that's articulate using those components. So you can see the concepts of building physics in the center to the different components of assembling the computational model on the outside. And then this is what the model actually looks like with those components. And up there is what we were working on. This is then modeling the first version, right? Not the second version I showed, but this is modeling the first version, which became the baseline. And ultimately looking at when there was no flow, when the flow increased, all the way to a significant flow, and then the different levels of pins. We tried pins with glue, pins without glue, a whole different selection of ways in which you'd assemble it so we could understand when we assembled, came up with any other design, how we would be able to calculate the performance. So when I'm thinking about ceramics, I'm thinking about the computational model. And so the ceramic ultimately is the that's finds the building is ultimately what's left. It's left over, right? It's what we arrive at. The ceramic is not what we start with, but it's actually what you arrive at. So this is same comparison of all of those, looking for a difference that makes a difference. In some cases, you see very little differences between the two. In some cases, very big differences, right? So it helps us understand what really we should be targeting of all of those variables. Some of them are more important than others. So to test this out, we picked a building. This is Stevens Institute on the Hudson, which is a building desperately in need of a new facade. And so this goes back to the era of concrete block behind stone with single pane monolithic glass and no thermal buffer in the mullions. So it's a very poorly performing facade. It is indicative of many facades from the 1950s that you can find all around the world that are currently failing and in need of replacement. And here the idea was to replace this with the new system. And so here is the baseline. So you start by modeling the baseline, including a system that you might use to work with the building. The idea originally was to capture that energy, use it through heat exchangers and storage, and then put it into a 2 or 4 pipe system that's already in the building. And I'll talk in a minute about why that doesn't work. So the spandrel panel is the target area for the system for replacement. And then we wanted to benchmark that against an ASHRAE designed curtain wall. So as normally you'd say, okay, what do we have to upgrade it to perform today? It would be this design. This would be the standardized and accepted way from ASHRAE to say this is the performance facade. And it would work a little bit different because you'd add new mechanical systems. So it has a mechanical system that's a little bit different, upgraded from the original one. And then the system that I'm working on. So this is deployed, the first unit that designed in the spandrel panel. And in this case, we thought from the temperature, we would get a lot of energy, and we just put that energy, and there's a lot of energy there. We put that energy right into the system. The problem is modern mechanical systems are meant to use things that have been on fire. They're at a much higher grade energy. They're either much colder or much hotter. A lot of energy is put in to the mechanical system to make it very hot or very cold to distribute. And therefore, ambient temperatures that you can collect in and around the building are not sufficiently able to connect into that system and make a difference. So in the end, we realized that we had to decouple the system completely and say there is a mechanical system. There's 2 mechanical systems in the building now. There's one on the building facade that deals with the bay in, and there's one on the core that comes out. That's more traditional. The goal is how much smaller can you make the inside system to save cost over time and make the building perform better by taking advantage of what's already in there. And so here modeling the same way, this is annualized. So power per area of an inlet temperature of 22 Celsius versus power per area of ground temperature, because we're not sure where we should start with the temperature of the water when we look annualized. So we took 2 points in there, and you can kind of see the difference between the temperature you start at does begin to make a difference. And then we're looking at, what is it, cumulative energy over time, over the year on the top graphs, right? How much coolth do you create, and how much heat can you create from the energy extracted and energy given with the system, modeled and then calibrated physically. And so these are the findings of the first tile. So there are significant improvements over the 1950s envelope, which is great. That's the column here that says savings, right? That's savings over existing. The savings over ASHRAE are less. Although from a heating perspective, even in this first iteration of design, it's still almost 15% savings in heating energy. That's not insignificant. In cooling, it's a little bit less, 6.6%. Fans, it's less because now we're pumping fluid instead of air, which is much more efficient. But pump energy goes up, so it kind of offsets from the savings. And heat rejection is 9%. So that's not nothing for a first chance. The point of the project, in total end uses, when you begin blending that together for a typical floor zone, is about 5.6%. So it's not a mistake, it's something. And it's indicative that we should go further and continue to refine the design. So ultimately here, if we're comparing now by the Bay zone, we can improve that a little bit. And then I'll talk about some of the design iterations. In this case, now we design the mechanical system as now separate in the model from the building mechanical system. And these are where the building physics components and variables that we care about are arrayed in the model. And ultimately, why we changed manufacturing techniques. Manufacturing the individual tile is significantly more intensive than it is to extrude tiles. So in our case, we moved towards an extruded model of tiles on the lower end because you can just make a significant more of them much faster. So on the top is the first tile, and the second is the next iteration, which is extruded with caps and the embodied the embedded heat transfer pipe. And here you can see the performance between the two in a kind of pattern graph, where you can see that what's important on the newer one is the balance of cool versus heat is significantly better than on the other one. So maybe the one on the right works in some climates where coolth is the problem, but on a balanced climate, like New York, for example, and I think here as well, you're going to want something like this because you're going to have shoulder months and a warm month and warm months and cold months. So you're looking for the more balance. In this case, you get more facade coverage and much more collector surface with this design. We realized that you needed more collector surface and more transfer surface. And of course, at the end, it's the facade, so it's the brand of the building. And so we want to make sure it's not so restrictive as you wouldn't use it. It had to be flexible. So we built this into modules so that you could pre-assemble the system. So it is a mechanical system or an appliance, a facade appliance, that can be deployed in very straightforward ways. You can see the kind of middle column up there, the kind of individual 1.5 meter wide sections. And the bottom, you can get the same window wall ratio with significantly different patterns. So there is the ability to create and say something with the building while it performs. That was important to us from that aspect. And so you can begin to look, you can see a bunch of varieties like this, how that might be deployed. So we also felt that it could be improved even further by changing the design to do both a heating loop and a cooling loop separated at the building envelope, which was the ultimate design. And so projected, we believe that we can increase that. In this case, we're showing a heating improvement over ASHRAE of 27.5%, and that's very significant. So this is one now we've designed, needs to be at some point in my life, if I get time, I will build it and test it and see. But there's a significant difference now that show that you can actually capture that energy, hold it in storage, and use it and create that ceramic mechanical system at the envelope. And so what we're really targeting here, this is some of Xiaofei's wonderful handiwork and graph, is the original, the top shaded area is the original. The offset area is that target. It doesn't look like a lot, but in some cases, like here, we can see big differences. Right? So annualized, it gave you the percentages, but again, that frequency plays a big role into how well it performs. So this is looking at New York. You start to see the differences here. This is Amsterdam. This is much bigger differences here in Amsterdam. And then this is Phoenix, right? You can see the center is not the issue. It's not the winner. It's on the other side. You can see where it makes a big difference. So we wanted to test this and see how much gain loss could you get in the different ones. And ultimately, I think this tells the story the best. The shaded area is where we started, and the line area is where we ended up. And that's the savings you get. That's the amount of camouflage you can get out of the building, out of this system for the building. And that's the final prototype. You can see the heat, we removed the tile and you can see the heat transfer pipe. Still the radiator on the inside. And that would be a model of one of those bays. And that's the final design where you now have the tile on the left was the first one. Actually, that's the one we modeled. The one on the right is the improved version, which has a thermal break between the hot loop and the cold loop tile. So that's the one we think is the best. That probably beats 27%, right? And that, why is it important to do that? Because buildings are often in heating and cooling at the same time. So you need to be able, at the envelope, you can't exchange through the same surface at the same time. So you have to be, and you have to be able to understand that my zone on the east and my zone on the west might be quite different. So one of these might be in heating and one of them might be in heat rejection, right? And so that's now the new concept of climate camouflage. Okay, last, what are we doing on time? Okay, right? This is a very small section, so we can have some time to discuss. So we did a competition a few years ago to try to put all of our thinking into how we would deploy, build a building in the similar ways to both the idea of decarbonization through an improvement of energy, as well as the articulating of fluid through the building envelope. So this is kind of bringing it together, not ceramic, because it was a metals in construction competition, so therefore we use metal. I guess I'm starting with the conclusion, right? We looked for, you had to pick a site and build a tower. We decided to build multiple ones. This is now Staten Island, which is often the forgotten borough in New York City. But actually, it actually has one of the best views of New York City because it's unimpeded from the south side. And there's a ferry station there that's pretty wonderful ride that you can go back and forth. And so we were looking for land that we could maximize. So we built the buildings in between the ferry slips. In this case, we looked at taking fluid from the bay in a fluid exchange, bringing it up into a steel facade with a heat exchanger and running that fluid around the outside of the building in multiple fluid loops, not dissimilar to the way in which we showed the ceramic, but in this case, you're heating and cooling metal surfaces on the inside and the outside. As the primary structure here is also the major heating and cooling engine. We optimized that structure for of course, gravity, but also for views and shading. And so in this case, it goes like from the kind of you see the material mass and the structural stability. It starts with stick framing, move to flat sheet, move to folded sheet, move to folded sheet plus tabs, and ultimately folded sheet plus stiffeners. We worked with our structural engineering team and did the structural analysis to show that we could build a building like this with this pattern. And so the building does change, that section does change all around the building from where you were. So this is showing how we would engage with the bay. I don't know if it's important, but it's at least a rule that you cannot change the water temperature around your building more than 5 degrees. So that heat exchange has to be done in a way where there's enough surface area that you only have a 5-degree difference when you're using it, but you can use it. And there are a few buildings in New York that do bring bay water in through their building to do heating and cooling rejection. And so this was just taking that same idea and bringing it now into the building facade rather than into the mechanical room, where the outside of the building is that mechanical system. And understanding working with Tishman, and this is why we're a multidisciplinary company, and this brings us back to the beginning of the story of why I'm at AECOM, is because it has all of the different disciplines under one roof. So I can talk to my mechanical engineer and my structural engineer and my contractor and fabricator and have them all help us create something that has never been done before. And at first they'll be like, you can't do that. And I'll say, you're sure? And they'll go, well, I don't know, maybe I'll do it like this, right? You just got to get them engaged in the conversation. And then all of a sudden they're like, we're going to bring a barge in and we're going to bake these in pieces. And then all of a sudden they take ownership of the component. And that's really exciting to see. It happens when you give them a challenge of something they haven't done before. I'm very used to that because I hate doing things I've already done before. So I always like to take on a new challenge. they're often very comfortable doing something they've done before, but when you give them the opportunity to see what it's like to go on that journey, then they really want to go with you. And so that's a big part of being the integrator in that dynamic from a behavioral perspective, is getting those people focused around doing something new, like they did at the Jet Propulsion Laboratory in NASA. This has a similar idea of embedding that mechanical system, now completely distributed airflow throughout the facade in the spandrel panel. An open layout, so everyone has a view in the office. Widest shape. These are all the different pieces, all the different criteria that went into the building design from a conceptual perspective, both qualitative and quantitative. This is an ovaloid, a particular shape, ultimately because it's more efficient from an energy perspective. Better views, easier to heat and cool than a same system with a box, and much lower carbon. So in here, we're tracking the material weight, the embodied energy, and the embodied carbon, maintenance cost, and then the operating energy use. And you can see we have significant savings over the square building with the ovaloid. So it's not an ovaloid because we like ovaloids. It's an ovaloid because it performs. May not perform in other locations the same way. It should be a different shape. But here, the shape is determined by the performance. And that performance is qualitative and quantitative. So the Forgotten Borough, behold Staten Island. There's 2 commercial buildings, 3 residential buildings we proposed to be in between the ferry slips along a park that they've been developing. There's a mall there before the city. What's interesting about this is slowly over the years in New York's already full, right? Manhattan's full. Brooklyn has slowly become filled with tall buildings. New Jersey's become filled with tall buildings. This is the last spot in front of New York City that has no tall buildings yet. So we know it's coming. And this is really the last slide, and how we envisage being in and around a space, in and around space like this. Thank you.
I think it's action of the research work. I said, we can find a large PhD thesis. We can subdivide the topics. Because you already did research on it over the past 20, 30 years, and it's improving a lot of models toolbox. You can see that it's very deep. The apps, you can see this passing skill, improving the and it's very ranked scope is actually established. Mainly focus on the carbon, experience. It's more performance based design. Yes, I'd like to first suggest to the pedagogical system how to navigate we have different backgrounds.
Yeah.
Before coming here. And I think your method have very general which is actually based on the automatic thinking and also the visualization process. Mm-hmm. And in the back given by some infrastructure and also the system and how to always kind of communicate the objective goals on one platform. It's very simple, it's one screen. You can see kind of parameters and inputs that could be changed, and all the way simultaneously give us the feedback to optional. It's very efficiently those two. So very directly negotiate with stakeholders and designers, chapters. It's all see very directly. It's not easy. It's based on another word. Yes. So I think how to develop such kind of platform through practice, through process. I think you have a very general methodology, and also you are facing with different project, but it's always go to a very simple working flow, working methodology. So my question goes to how you organize such kind of framework in your team, how to develop different team members, and because you're serving for different people,
Yep.
Different, sometimes clients, sometimes designers, sometimes very sort of very specific structure. So I think you're looking at it.
Yep.
It's very simply into one platform. It's difficult to abstractly develop method. Actually, it's a visualization. It's a dynamic vision. So my first question goes to, it's a very general platform. How do you organize it?
Yeah, that's a great question. I would say there's a couple ways to talk about that. One is understanding motivations of the participants you're working with. What are they, both stakeholders want something out of this. They have certain criteria that they need to hit. The disciplines, when any design project of any scale is very messy. It's what I call a fractured stakeholder base. So the motivations are different from the owner, from the contractor, from the engineer, from the authority having jurisdiction that's approving it. Everybody has something different. Our job is to be able to bring those pieces together. And that's why the dashboard is kind of general, because it's trying to reference all of those different parts and put them and make them on an even plane so that all of them are contributing the same to creating something that each of them individually couldn't create. So that's our work, right? What the role is then specifically, we call it, Maria, who's our global principal, calls it radical collaboration, right? Bring everybody together in a room like this. And the goal is to move from real-time conversations, hey, let's talk about this system all together, to, hey, let's calculate that system all together. And that does something very different. When you say, well, I think we should do this, and if you have that integrated project delivery, mechanical team says, yep, we've got our idea, we're going back and do some calculations. But you say, no, don't leave the room. Say right here, input the information. Now let's all together look at how all of the things we care about change because of that. And when the group sees that, the group dynamic reads the project differently than the collection of individuals. And that's a paradigm shift in terms of how people collaborate and what the results are of that collaboration. When you can see how the lever that you care about impacts all the other levers and get feedback instantaneously, that's a very different experience. So the methodology is really about creating that change in the room. It's about behaviors of people more than it is about the calculation. Because what we know is the calculations will change. They'll get better. Computers will get better. Soon you won't need to put anything in. You just say, give me the best design, blah, blah, blah. You'll read it out and some computer will spit you out a design, right? But what we really care about is, are people's needs met of all those different stakeholders, and are they feeling able to contribute? And when that happens, then it's a different process. Then they don't want to leave the room and go back and do what they normally do. They want to go on the voyage with you to someplace they haven't been. And I think everybody wants to be in an adventure, right? And so that changing the way in which we work and the types of conversations we have is team by team. And so then the second part is how do we do that? It's really by embedding ourselves within a team for a project. Has to be on a project, has to be real, right? It can't be made up. I mean, this is made up for sure, but it's still a real place. Most of the projects we showed, all of the projects we showed in the beginning are real projects with real clients, with real high stakes, have to be tested on real projects. And then for us, it's to take them and embed ourselves with them and create converts. So from a practical standpoint in the practice, it's work with us and now you take it and go. And we've had some really good examples where we trained a team in Madrid how to use this tool for building. They workshopped it and came back with new and improved modules that we didn't do. And they said, so that's like an evolution. right? So now it's kind of, there's an evolutionary biology component to it. I've given you something of these components. They take it, digest it, and they give it back to us better, right? And that's what we're starting to see is an ecosystem working all towards the same goal. So from a pedagogical perspective, it's part behavioral change in terms of how we do something. It's that radical collaboration. And then it's allowing change, also being open to change, right? Allowing it to come back to you and you to be influenced as much as you've influenced.
So in terms of the radical collaboration, sometimes it's not at the very beginning of design phase. It's a conceptual design. Normally, it's not always goes through very quantitative decision. Yes, very qualitative decision making. So I want to know such kind of toolbox and is that what kind of platform can you describe? It's a software platform, or it's open all the way to the design teams, or every time you should modify a bit based on a very general platform, because the design problems and project program are different, right?
Yes. But the model, we typically, we work early stage, day one, we try to understand the project and understand what's new about it. Typically, we'll go back and custom design some modules. I'll give you the example of the laboratory building. That has two types of mechanical systems, a regular office mechanical system and a lab mechanical system. They work really differently. So we had to design a module to take account for that, those two different systems. But we worked with the architect every day, right? And so they worked on a model that we could import or we could mirror, either way. And so it's not about taking something and giving it back, but it's about working together, much more like software development, the agile development process, which is cyclical like this. It's instead of this, which is architecture and design, right? We do it like this. So that's the other fundamental change. How and where does innovation come from? Software and technology companies. They are the ones who created that radical growth through innovation. Their method is agile. So our thesis was, why don't we design agile? And so in order to design agile, we needed this platform for people to come in and out of to get results and allow it to influence. And so the concept, even the concept tags brings with it quantitative information. We have to start with that. Say, even any line you draw has quantitative information, has meaning in the physical world. If we accept that, then you're starting off with enough information to start that cycle, that kind of agile cycle of design.
Yeah. Because I think it's a very good graphic for us in the education. Students actually originally teaching students how to make design, but it's just about the result, renderings, functions, all these kind of things. But from the past few years, we start to teach them how to develop some toolbox. It's like contribution. It's like a ways of recommendation to conclude how to see from parameters in the context. So I think your very advanced work during the design process, but mostly AECOM can do such kind of work. This is super big team. Right? It's a very detailed subdivision team. In China, the design institute, sometimes the team is not very small teams. It's your people. Project super efficient, super shut down. So I mean, how to change the pedagogy in terms of future transformation, because already goes to the high performance to high quality buildings from the national strategy. So I think it's super important if your thinking switches from general softwares and open to
Well, we actually are. We have a thing called what we're developing now called AECOM Zero Cloud, which is meant to be used not by specialty teams, but by everybody. Yes. But I also think there's a couple step process, right? What process we're showing is really machine learning. There's the next step is automation. And when you have automation, then a few people can do a lot. So you automate the things you don't need to be involved in. So we're starting to work through the automation process. And the final stage of that, of course, is artificial intelligence. So we're going into that full speed, but also eyes wide open and cautiously. But we're trying to do that in measured steps. So we already have the machine learning and the ability to fetch information, which is about getting results, as much results as you can, but not necessarily the best results. The automation is about getting accurate results, right? So we're moving towards accuracy, that a few people could get broad, accurate results. And then the next step with AI is about effective results, right? So with AI, you should be able to make, it's not the most accurate, it's the most effective. Because in the end, you don't want the most accurate building, right? What's the most accurate building? You want the most effective building. So we know where we're going, right? We kind of have that point on the map, but we have to go in measured steps because the technology is changing very fast. And we're trying to understand how we embed them, what's the difference that makes a difference. But I do think that's the pathway we're going. And it's important that I think it is not in and of itself, it's a workflow. I can't find a better way to say it than a workflow with a technology layer. I'll work on that. But that's the thing that you're exporting, right? But we all learn methodologies, right? And how we design. This is just a different methodology, right? So I think with the right amount of automation, then I think it can be used by many people and not just by a few.
Yeah, I think it's super attractive because your work based on the past 30 years research. So if the next generation can stand on your shoulder,
please, yes,
a lot of energy and time.
Yeah.
I think
yes,
already very high end. I think structure of thinking process is super interesting because you're already very abstractly very clear, although it's very complicated.
but I appreciate that vision very much because I feel like I've had the opportunity to stand on people's shoulders, and my goal as was an educator, and I feel like we're doing that in our group, just in the kind of enterprise context, is we want the new generation to stand on mine. I couldn't be doing what I'm doing if I didn't have Xiaofei and his colleagues. Can't do it. I can't do it. I know what all the things can do, but I can't do it myself anymore, right? It has to be. So there are now people who are here and bringing it to places that I can't go. I am now along for the voyage, right? So we just can kind of help push it along.
The systematic thing is right. But for example, our PhD students, we just focus on very narrow topic. Probably what they need is actually based on a framework and make some further.
Yeah.
That'll be helpful for them. And maybe that can be contribute back to the general system, adding more programs or adding more functions to this platform. So that's like the ecosystem. And if you can establish something, I imagine, because it's super good and super has different skills, that's great. With different planners, structured designers, and also including architects. And maybe all the way goes to design and
Yep.
So I think every one of them have their own toolbox. Some of them just like 1,000. So government sometimes, some of them like 20,000. So small toolbox, big toolbox. But what we need, and we make a discussion, is the platform.
Yeah.
If all this kind of research goes to one general thing, that's, I think globally we need something like that.
Yeah.
Right?
I think that we're finding that the data lake, right, is one of the most key things. You'd think in a company like ours, 50,000 people all over the globe, we'd have a huge data lake. But what we have are a lot of data ponds that aren't connected. And so we're realizing that to really be able to do that, to pool the data, and we're only a small, 50,000 people is tiny compared to the world, right? So we need to create ways in which the data can talk to each other. So we already have to restructure the data within our own company. When you start from scratch, you get to create that. I think we'll see very rapidly standardization in how that data is leveraged and managed. And then all you're doing is querying the data, ask the data a question to get out good information. So I think we're in that process, that standardization of what that back end is, how that data lake is captured, managed, right? And then how it's queried is, in a software sense, is already starting to be managed, but in the AE, architecture, engineering, construction environment, it's not quite there yet, but it will catch up. And that's why I really feel like taking from software, taking from technology and looking at those processes is critical to understanding how we can operate most effectively when we realize that everything we do has connected to everything else in some quantifiable or qualifiable way. The other thing I think that's really valuable for PhD students, and I thought a lot about this, why am I doing a PhD rather than a doctor of design, right? Or a doctor of engineering or a science degree? It's the philosophical component. And I took that very seriously. I wanted to do it in a way where I had to, at the end, contemplate meaning. So I would connect that very narrow thing to something much bigger. If I didn't take the time to connect it to the bigger world, then I was focused, I was more like doctor of engineering, right? Or doctor of architecture. I wasn't a doctor of philosophy in architecture. So if you take the philosophical component very seriously, and you just know that it's there before you end, or at some point you go back and say, what did I do? What's its meaning? How is it connected to other things? That's also something that I think is very, very important because it places your very narrow focus, and it has to be for PhD, narrow focus, but in context connected to many other things. And that connection is also kind of a simile to the idea of the data lake, right? We're feeding in together. So you should be aware of what's next to you and what's around the corner. And that can be a component of the work. You can't do it all the time because then it's a philosophy degree, not a design degree or engineering degree or science degree, right? But to contemplate the meaning of that very narrow band, I think is critical.
So in terms of some big model, it's very generic.
Yeah.
Do you think building technology?
Oh yeah,
Big models.
it's going to happen. I mean,
What kind of framework?
yeah. I'm aware that Google had tried to do this early. It was too early. It just wasn't there yet, right? This is like 5 or 6 years ago. They're like, press a button, write a sentence, and get a building, right? Okay, so the technology wasn't there yet, but it's there now. So it's going to be a short amount of time before that happens. The question is, how, at the moment, it's hard to contemplate replacing judgment. There's a lot of things you can replace, calculations you can replace, but replacing judgment's the hardest. Maybe that will happen eventually, right? Replacing judgment is still in science fiction. It's not speculative fiction. It may happen, probably will happen, but for the moment, I think we can focus on how do we refine our judgment, because a lot of those back-end tasks are going to be taken care of that we normally work on all the time. Our production is not necessary anymore. It's, paper doesn't have to be on the site, right? If you choose not to be on the site, you can just walk around with your device. So that's happening pretty quickly. So then what is it that we really do? It's our judgment based on the things that we see. And that's why you see the diagram work that I do, the amount of diagrams, why I'm collapsing a lot of numbers and diagrams and things, because in the end, I'm trying to get the things in front of me that in the end I can see it and judge it, right? I'm judging this is right or wrong, good or bad. And that goes back to the kind of artistic nature.
Human engaged process
Yeah.
to make decisions step by step. It's a kind of control by the collaboration between human design. Right?
Yeah.
So my question goes to, if such kind of process can all the way go to a black box, or part of them could be black box decision progress.
I think so. I mean, I'm always concerned a little bit about the black box. I've done some black box work and I get good results, but I still have some concern. And there's a few tools out there that use a black box, and I'm concerned about those because I don't know how accurate they are. And one of the reasons we're doing what we're doing is because we feel like our process is probably right now more useful than the black box method. But I don't know if you believe me if after showing all this, I tell you that one of the goals is to actually create more space in the process for judgment and contemplation, so that the human condition, you actually create more space. Like the amount of time you actually design on a project is very small, right? So if I can take all this other time and compress that, can I get a little bit more time to contemplate, right? I mean, ultimately, the goal of technology 100 years ago was to create leisure time. Oh, I'm great technology will do all these things for me so I can have leisure time. But leisure meant something different 100 years ago. It meant thinking about things beyond food and shelter. It meant thinking about meaning. So I can, I don't have to work all day because something's working for me. So therefore I can think about other things besides hunting and gathering, right? And therefore that's the philosophical component that defines us as humans. And ultimately design is a humanitarian discipline. So if we can create, the altruistic idea here is to use enough technology that you can actually spend more time thinking about the right thing to do, rather than, being rushed through your design and then have to produce. So what does the black box do for you? Maybe it allows you more time for contemplation and the artistic side, and putting more of the human actually back into the work, because you've taken, the machine can take the rest out for you. You don't have to do it. So I'm hopeful. When I'm optimistic, on the days I wake up and I'm optimistic, I say that's where I think it could be.
I think also some of them focus on robotic fabrication industry. So I have a question goes to because China are different. I think still in the whole world is still a very strong gap between the planning research and the fabrication technology and competition. Because the company now goes all the way to this kind of custom facade, which is everything is actually that's last solution is actually the future solution. Global is not easy. It's still a very big gap in China. Globally, what's your thinking on that? How to bridge this gap?
Yeah, that was something early on in the work that I was thinking a lot about. Do you make each individual piece, or do you make a mold that's very specialized that can make many pieces that perform? In the end, I came to the conclusion that the latter was more valuable, that I make a highly articulate mold that can do many things versus many different molds. And if you've spent time doing CNC manufacturing, it's actually not fast, right? I can cut a piece of plywood much faster than I can mill a piece of plywood, right? With a table saw in my two hands. So the speed of fabrication by hand is faster, but it will do less. So the idea is if you can put a lot of energy into a repeatable component, perhaps that gives you both, the best of both. I think factory assembly is going to be part of the future. I think that allows for robotic assembly to be more useful rather than robotic assembly on site. I'm sure we're going to see that too, but assemble in the factory. That's got to be huge. And what factory assembly allows you to do is mass customization, but within a limit. And so understanding how much customization is too much to make it inefficient versus how much makes it perform better. So there was some, these are protocols that have been around for a little while, and I would have imagined it for this building. So instead of each piece being different, I would say you get only 10 pieces, but you have to put them together in the right way. I'm not saying we did it here, but that's the thinking, right? So even right now in the tools, you can make a model like this, and then you have to say, well, that has 10,672 pieces, different pieces. Can I do this in 52 different pieces? And you can use a protocol and do that. The shape will change a little bit, but it won't impact the performance enough that makes a difference. So being able to understand what the right level of mass customization is as a standardized method of design rather than a specialty, because right now it's a specialty to do that, but standardizing the fact that you reduce the amount of parts. And that's really what industrial design does, right? Design for manufacture. Doesn't mean don't customize, it means design for manufacture. So customize within the limits of the goals at which you need to. Again, borrowing not from our industry, but from an adjacent industry and how they do things, and bringing that in to how we can learn from those adjacent industries, how they're able to do that, right? Mass customization works because it doesn't do everything different. It does just enough different for it to make it perform uniquely.
We have a very strong reference also to pharmaceutical shop.
Yeah.
And we actually pay rapid research on their projects. I don't know.
Yeah, I know them. I know them well.
Over the past few years, what's happened has COVID, we don't visit too much. Because their strategy actually based on their fabrication.
Yep.
And they are also very good at design.
Yeah.
And we bridge these two things very well. So we have a very great pattern over the past few years based on their strategy.
I mean, they originally, before COVID, they were able to do this kind of. I mean, I've heard Chris Sharples, one of the partners, speak about this. Well, I used to work with his wife, Anna Dyson, for many years at Case. She was our director at Rensselaer. And I've heard him speak about this often. It's really interesting. He would talk about it as temporary factories. You don't need to make a factory and ship everything. Make a factory locally for the time at which you need it, and then take it apart. Move that factory to where you're building. So the idea of mobile factory is a kind of really interesting way. I think they're still projecting that. I don't think they're doing that yet, but that's the concept I think they want to work towards, and that makes a lot of sense to me. There's still so few modular kit of parts buildings out there. There's still a lot to be done to overcome the challenges of a traditional construction assembly and a factory assembly, and putting them together, you get all kinds of problems, right? But those will be solved the more we do, because we're going to continue to see that, oh, the steel industry means you need enough tolerance when you put your piece on there. So I think those, you just have to do more of them, but that's where they're headed. The way we've been thinking about it is like the car industry. So again, another adjacent industry where Volkswagen, I think, did this first. I think every car industry is now on it, which is a platform that has just the right amount of adjustability. So you can have all of the different brands in Volkswagen Auto Group using similar components where they need, and then upgrading to where they don't. Engines, transmissions, interior finish, frame, all of those things are now, and you want to build your car, you go to the digital, you select, these are the pieces I want in my car, that's the car, and I can have a Seat, I can have a Volkswagen, I can have an Audi, I can have a Porsche, I can have a Lamborghini, but they share certain parts that are the same. It's very efficient to do that way. And I think we could learn a lot from that. We've been trying at AECOM to do that we were trying to do that with OVG, the project I showed kind of in the middle, because they were very interested in this idea of, we call it space data objects, right? You say, we know what the objects are, we limit the amounts, but then we pick and choose by project to assemble something unique every time. So you have to know just the right amount. So there's clients out there who are interested in that, right? Who are willing to take that journey. We just need, at this point, we need buildings to want to do it. So I think both those are good ideas. I think the idea of the kit of parts that are mass customized and the idea of the mobile factory, both are valid because it's evolutionary. We need to try all of those methods to figure out which one really, we don't know what the solution is. So therefore we should try them all, right? And see which one seems to work.
The last question was the case, because I think it's even actually average early special role. Which is what's crucial to us, because we already said students, some of them achieve some of the students in the city, they all have the right feedback. So kind of more one research I think that's kind of potential future.
Yeah, I think it is the future. One of the things we've been thinking about is, instead of bringing people from industry into the university, we think we want to bring the university into the industry. So that flipping that reverse. I proposed it a couple of years in a row. I'm still trying. I just need to get it approved. I would like to run a studio in our office, right? And that changes that dynamic. Rather than bring me here, we bring you there, and then we work on a project together. And I do think that has to me, I still feel like that's the future for education and probably the best way the industry can grow. Because the industry is too far removed from research. Right now, it's very different. We can't call what I do research, right? We're not the research laboratory. We have to call it innovation, right? Because no one wants to pay, clients don't pay for research. Clients pay for innovation. So we need to bring that closer, and it has to be collaborative. So it shouldn't be separate. And I don't know in the previous models where it was like, oh, let's bring the professionals in to run a studio. I think it's different. I think you bring the students in to work on real projects, and then you get the same thing out of it, but maybe that reverse is different. But I do think that we need to see more of that. The industry needs to grow. It's only going to grow if you bring in disciplines in the university doing the cutting edge work with enthusiastic students who want to come try things out in the real world. And I don't think that the universe is not real. It's very real. It's just different, but we could bring those things together and they could be one thing. And CASE was able to do that in its own model for its time. It's continuing at the Center for Ecology and Architecture at Yale, which Anna now is running over there. So it continues to grow, and CASE continues to grow. We are going to try to figure out how we do that at AECOM, like how that works. I think the collaborative model is the way. I think the model of funding the university is harder now than it used to be. So is there another co-beneficial arrangement that can be made? I'm sure there can be. I'm sure there can be.
Thank you. Do you have any questions? Yeah.
Rodrigo has already covered some of my. I want to dive deeper. I'm very curious about how many members are in your core team and how much time could you spend to very useful job. Last year, Shopee gave us a lecture about this software, and I think that it's almost it's 90% similar to your presentation today. And you just talk about your vision, like artificial intelligence and automated.
Yeah.
I'm curious about what latest year for next year.
Yeah, some of those pieces are new. We've continued to build the platform, and we've been moving towards this idea of bringing it to the cloud. That and integrating in artificial intelligence directly into the model, so that we can get information directly out. In other words, creating a large language model and then referencing the large language model to get new information out of those same things. So that's what we're working on currently, both making a more openly accessible version, but also one that we can start to use large language models as a key component of what we're doing. So every time we do a project, we add a component to it. There's always something new that we're building. That for us, it's, you can use artificial intelligence. We've already done this, and it's just, to me, it's just not that exciting, which is to say, great, render, we made all our selections, and then we render it. And then you get a building that looks like a building, but it has more solar or less solar. It's okay, but the rendering is not as interesting. What we're trying to do is, can you use a large language model to create a 3D assembly of those systems as a diagram, so that it can be used to really generate functional design components rather than single line diagram components. So we think that's something we're working on right now. So turning that into generating an actual design that you can then detail and build. Rather than an indicative or direction finding, it then actually becomes a design delineation tool using AI to assemble those components for you. So that's where we think it's going. That's what we're working on. And we don't know the answer yet, because I think it's very new, like trying to assemble these things. So we're still trying to figure out how to do that.
And you talk about Delta.
Which one? This goes back a lot, right?
Annual temperature.
The climate tape.
Climate tape, the original one,
The
or the last one?
jumping. No, I think the very first one, they jump into the research section.
Go all the way up. Oh, not that far. This one.
No.
No, not that one. You meant the one down here at the end? Yeah, heating degree day, cooling degree day.
So the area, the red and the blue part. The area is
So the blue part is the amount of heat, is amount of cooling, and the red part is the amount of heating. And that area represents the amount. So it's representative, that volume, what you see there is that area is representative of the amount of it and the fluctuation. So it's combining a couple different things together to give you an indicative graph. So it's about the frequency and the amount at the same time. So it's not necessarily numeric, although there are numbers to it. It's tracing those two things together to give you an indicative understanding of the amount of energy. So it is kind of a new way of representing something.
Yeah.
It's not as simple as like how much heat or how much cooling. It's heat, cool, frequency together. So it's an indicative pattern. But it is indicative pattern created from a numerical model and weather tape. So it's doing both of those things. So
it's not very accurate. It's more like.
So why is the one circle should represent the amount?
That's
Why
just
not?
another version of
it's another version of the same thing wrapped in a year annual clock.
heating cooling degree days are just one step before the actual energy consumption that we're calculating, but it's more, straightforward to understand the beginning of the concept of design phase. How much heat, how much cool that we need to make the building comfortable.
I think this kind of.
And to answer your question more specifically, it's not accurate, but it's effective, right? The goal is to communicate that difference. That quantity is real in there. It's a real quantity. That proportion is correct. And it's about understanding that proportional quantity as that's the actual thing we care about, not the numerical value. It's how much. Because my question at the very beginning was how much? Well, that's how much.
That could be a PhD thesis.
Yeah, no, you're right. I 100%. And that's, I think there are things in here that, again, someone needs to stand on these shoulders and do that component. Yeah. Yeah. Yeah.
Well, no, this is a great research.
And not that I think this should replace accurate modeling or prediction, but I do think that there's a way of communicating information that is both qualitative and quantitative at the same time that allows you to make your point that that's how much. Right? It's not this much or this much, it's this much, right? It's precise, but not accurate. I don't know if that makes sense.
Okay, thank you.
Thank you all. Thank you for your time.